Alright, so let's take a look at and summarize some information about making electron configurations. We will take a look at the Pauli exclusion principle, the Aufbau principle, and Hund's rule in writing electron configurations, and we'll write electron configurations using the noble gas notation, and we'll identify exceptions to the orbital diagrams and electron configurations. An electron configuration will show how the electrons occupy the orbitals around an atom and around the nucleus. In electron configurations, we have the S subshell, which holds 2 electrons, the P subshell, which holds 6, D holds 10, and F holds 14. When we do electron configurations, we first have to follow the Aufbau principle of filling, where each electron occupies the lowest energy orbital available. This shows that if you write out all of the subshells that are present in each of the principal energy levels, you would have 1s, and then 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then so on. And then we draw the diagonal lines to show how they will fill. So we'll fill first the 1s, followed by 2s and 2p, followed by 3s, 3p, and then down to 4s, back up to 3d, 4p, 5s, back up to 4D, 5P, 6S, back up to 4F, and then so forth. This is another representation of that, so we have 1S, 2S, 2P, 3S, 3P, 4S, 3D, and then 4P, 5S, 4D, 5P, and so on. This is an orbital diagram that would show the sequence of filling. It's the same as what we have talked about before. The other two rules for electron configurations are Hund's rule, which means that you have to fill each equal energy orbital with 1 electron before doubling up. So inside of the S subshell, the P subshell, the D subshell, or the F subshell, all of the electrons need to be in their own orbital unless they have to. This is like the school bus rule. You don't want to sit with somebody else unless you have to. The Pauli exclusion principle says that a maximum of 2 electrons can occupy a single orbital only if they have opposite spins. So let me show you what that looks like. So if this is our neon atom and we were going to do the orbital diagram, which is already filled in for you, we would have filled in 1s, we would have 1 spin up, 1 spin down, and then we would have filled in 2s, 1 spin up, 1 spin down. So that's the Pauli exclusion principle, where they have opposite spins. And then this is Hund's rule. In 2p, we would go 1 up in this orbital, 1 up in this orbital, 1 up in this orbital, and they all have to have the same spins. And then we'll only double up whenever we need to. And so this is following Hund's rule. So let's do a few examples. So we have our nitrogen and we have chlorine. So let's do the orbital diagrams and the electron configuration. Alright, so first we have to decide how many electrons they have. Nitrogen is atomic number 7, so it has 7 electrons. Chlorine is atomic number 17, so it has 17 electrons. For our orbital diagrams, I'm just going to draw lines and then show how many orbitals are in each subshell. So I'd have 1s, 2s, they each have 1 orbital represented by that 1 line. And then I have 2p, which would have 3 orbitals. This is all we'll need for nitrogen because we only have 7. So we'd have 1 up, 1 down, 1 up, 1 down, so that's 4, and then 1, 1, 1. Okay? And so our electron configuration would be, that electron disappeared, 1s2, 2s2, 2p3. Alright, for chlorine, we'll need a little bit more, so we'd have 1s, that has 1 orbital, 2s, that has 1 orbital, 2p, then we would go to 3s, and then we'll go to 3p. Alright, so if we fill this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And so our configuration would be 1s2, 2s2, 2p6, 3s2, and 3p5. Alright, so let's do some other examples on your own. So we have aluminum, which has 13 electrons, and vanadium, which has 23 electrons. I've drawn out the orbital diagrams for you so that you can take a look at what the order would be. So go ahead and fill those in and then write your electron configurations. You can pause the video and do that, and then I'll show you the answer. So here's your answer for aluminum, vanadium. And let's do 2 more examples. So here's carbon, atomic number 6, and iron, atomic number 26. Go ahead and draw out the orbital diagrams and then write the electron configuration. You can pause the video and then I'll show you the answer. So here's the answer for carbon and iron. Here's just a few examples of orbital diagrams for the first 10 elements. You can take a look at the electron configuration notation and how all of the electrons fill each orbital. Alright, so we'll talk about noble gas notation. Sometimes you want to shorten up the electron configuration, and so in this notation we use the noble gas in brackets, and that indicates that that electron configuration is all included, and then you just include the electron configuration after that point. The noble gas will always have a lower atomic number than the atom or the ion of the electron configuration that's being written. Alright, so let me show you an example for arsenic and for oxygen. So whenever we look at arsenic, arsenic is here. The noble gas that comes before it is argon, which is here. So we put argon in parentheses, and then we have 4s2, 3d10, and then 4p3, which is what I have written here. So let's take a look at oxygen. Oxygen is here. The noble gas that comes before it is helium. So we would write for oxygen, we would write helium in parentheses, and then we would write 2s2, 2p4, okay, which matches up with what we see here. Our next 2 that we're going to look at are tungsten. So tungsten is W. Alright, so let's do another example. We'll take a look at tungsten. And so with tungsten, the noble gas that comes before it is going to be xenon. And so for tungsten, what we would write is we would write xenon in brackets. And then we would go to the next one, so we'd have 6s2. Now it's going to jump, though, to these F sublevels, and so it would be 4f14, and then it will come back to our D sublevel, and so we would have 5d4. Here are some examples for the electron configurations for elements 11 through 18, and so this is going to be showing how the complete electron configuration would look, and then the noble gas configuration. Now for configurations, there are always a few exceptions, and so our exceptions are going to come in the transition metals for the most part. And so for the most part, we can use the Aufbau diagram and those energy levels to write our electron configurations up through about atomic number 23. There are some particularly transition metals. You need to know chromium and copper and silver. They will not follow the Aufbau diagram because there will be increased stability to have half full or completely full d orbitals compared to s orbitals. And so here are our exceptions. So we have chromium. Our predicted chromium electron configuration following the Aufbau diagram would end with 4s2, 3d4. But 3D or D subshells are very stable when they are half full or almost or completely full. And so the actual configuration will actually be all of those, that configuration, and then 4s1, 3d5. For copper and for silver, they're predicted for copper would be 4s2, 3d10. For silver, it's just the next row lower, so it's 5s2, 49, so copper is 4s2, 3d9, and then silver is 5s2, 49. But the actual one is that copper will have 4s1, 3d10, and so one of those s electrons is going to be moved to the d subshell. The same thing will happen for silver, and the same thing happens in chromium. An electron moves from the s sublevel to the d sublevel. This makes the d sublevel much more stable, and then what you should see is that all of these metals will end up with what we call one valence electron, which we will look at in another lesson.